Welcome back, everyone. So let's see one more way of finding the multiplicities, because there is already a count function defined for any list. So if you do xs dot count or list, any list dot count of a particular element value, then it will give you how many times that element occurs. Okay, so someone online has asked, is there any way of doing this by using some kind of count function? So yes, there is. Okay. So how to use this for extracting the multiplicities, right? So one way is I can go through the list. Let's just see if I do this, what happens. Sorry. We'll print the counts of all the values in the list. But this is of not much use. Okay, I can print the value as well as the count. This is almost what we want. The problem is here, the count is also repeated, right? So it shows 1, 2, 1, 2, right? 2, 3, 2, 3, etc. So yeah, make it a set first. Then we'll repeat the elimination. I think I forgot to bracket. Right. Yeah, not like this. So actually I should make a list of this. So what is right? So what is the way to do this? First of all, if I do x comma xs dot count of x or x in xs, that will actually give me this list. But in this list there are repetitions. So to eliminate repetitions, I can just do set of that. That gives me a set. And again, I can convert it to a set back to a list if I want, right? By using this. So again, this is one line way of doing the same thing, right? Using existing functions. So partly the point was to work out the logic by ourselves. But yeah, once you do that, this is a simpler way of doing it. Right? Many of the functionalities that you want can already be done in terms of what is already there. You just have to figure out how to do it using the existing functionality. So we'll redefine this, right? Okay, let it be there actually. There's no, I don't think there's a, well, actually I could comment it out in one line, not bother to do that. So I'll just redefine it. So not the first thing, this is not needed. Simpler one. You can keep it as a set also, but better to convert it back to a list because generally we work with lists. So yeah, still works. Okay, now you can of course apply this to the spectrum of a matrix. So there's nothing stopping you from doing that. Take the spectrum of a graph and apply this function. So this works for any list, right? It does not assume integer values or anything. It does not assume any numerical values at all. Whatever kind of list you have, you can do this, right? It's very general. Okay, so we were looking at Laplacian spectrum. As I said, the multiplicity of 0 as an eigenvalue. That using the count function, again, you know how to do it, right? So if you do dot count of 0, this gives you the multiplicity. So let's experiment with this maybe. Maybe better option is here. So depending on how you give it, it's going to give different kinds of controls, right? Slider or drop down. So you can see that indeed the multiplicity of 0 as an eigenvalue of the Laplacian matrix of G gives you the number of connected components of G. Okay. Many of these graphs are connected. By the way, suppose, so here is, I want to show you a variant of this interact thing. Suppose you have a large number of values here. You want to take this slider through many values, right? Up to some large value. You can of course click and get that, but again, you cannot click and get the exact value. So the problem here is, especially if this part of the computation is, you can already see that there is a lag, right? I've already stopped changing the controls, but it is still doing this. Why? Because it is giving the output for all those values, which I explored in between while trying to get to this 39. I had to go through many values. So it is giving the output for all those values, and now finally it has stopped because it was slightly heavy computation. It has to compute the Laplacian spectrum and then find the multiplicity of 0. So that takes some time for large matrices, right? So there was a lag. So this is inconvenient. So one option here is, if I give, let me try to remember, auto update. Yes. If I give in an interact widget only, not generally for functions, when defining the function, if I give the optional argument auto update equal to false, then it will not do this until I say run interact. It will not actually run it. So I can explore with the slider and find the correct value. So I can go up to 39 slowly, right? Here also can get the correct value that I want and then run it, right? So then it will run the computation. Okay. So until then it won't. Not only that, I can then again run it for the same values. So I need not change the value once and then come back. If I want to get another random graph for the same value, I need not change the value slightly and then come back. I can just click run again, right? You keep the same values and give me the next graph, right? Large number of these graphs are actually connected, although I've given 0.1 probability for the edge to be added. Yeah, because it doesn't take much for a graph to get connected. So to remind you, the optional parameter is auto underscore update, and you make it false. It is default, by default, it's true. You make it false, then the interact widget will not run automatically. You have to click run interact. This is useful if you have a large number of values in the slider. So you may take some time to find the exact value, and the computation also may take time. You can use this version instead. Okay. Okay, so what other matrices are there? Incidence matrix. So you have G dot incidence matrix. So G as well. This is G. This is the incidence matrix of G. So what is the definition here? The rows are indexed by the vertices of G. Columns are indexed by edges. And the ij entry is 1 if the ith vertex is incident with the jth edge, right? So what are some obvious properties of the incidence matrix as defined in this manner? No, columns are edges. Columns represent edges. Rows represent vertices. So every column will have exactly 2 ones, right? For a simple graph without loops, simple graph, right? Simple undirected graph you're taking. Every column will have exactly 2 ones because every edge is incident with exactly 2 vertices. This is also a way to prove handshaking lemma, which we saw yesterday. Proof is if you take all the row sums, right? Each row sum is going to be what? How many edges are there? Each in a row, how many ones will be there? How many edges that vertex is incident with? That many ones will be there. So if you take the row sums, that will give you the degrees. But if you take the column sums, that will give you 2. Every column sum is 2. How many columns are there? Number of edges. So if you take sum of all the column sums, that is 2 into number of edges, whereas sum of all the row sums is sum of the degrees. The sum of the degrees is obviously equal to twice the number of edges. Right? That proves the handshaking lemma as well. Mathematically, you can even write this. So usually we denote the incidence matrix by B. Okay. So mathematically, if you multiply B, right? You multiply B by the all ones vector. All ones vector with how many components? Number of edges. Because number of columns in the matrix is number of edges. So you have to multiply on the right when you're multiplying a vector, it has to have that many components, number of edges. Right. So if you multiply B on the right by the all ones matrix of the correct size, it will give you the row sums, as we know. Any matrix you multiply with all ones vector, you get the row sums. Whereas if you multiply on the left, then what do you get? Column sums. Okay. So handshaking lemma is basically the statement that if you do all ones vector, I'll just name it. Okay. So this is one of the all ones vectors, which I'm using on the left side. And this is the one I'm using on the right side. One is actually a row vector and the other is column vector. This is actually what? This will be sum of all the entries in the incidence matrix because I'm multiplying on the left and right by all ones vectors. But then I can read this 2 ways. I can do U star B, then that star V. Or it is at the same time, it's associativity of matrix multiplication. At the same time, it is equal to U star B star V. These are the same thing because of associativity. But U star B is column sums. Star V is sum of the column sums. Whereas the other one is U star B star V. B star V is row sums. So U star that is sum of the row sums. Sum of row sums equal to sum of column sums, obviously. But sum of, column sums are all 2. The number of, sorry. G dot order. Sorry. Yes. Here, yes. That's correct. G dot order. Yes. Right. So both of these are equal to 16. So then fact is this is u star b star v or else u star b star v, right? One is going to give you the sum of column sums and the other is going to give you sum of row sums. And then again, one of these is sum of degrees, the other is twice the number of edges. So that's algebraically the proof of handshaking lemma. Yeah, so that gives you the incidence matrix, and incidence matrix gives you this information. But there is one more incidence matrix, which is the oriented incidence matrix, or 0, 1, -1 incidence matrix. So for 0, 1, -1 incidence matrix, you give some random orientations to the edges of G. So okay, I'll not. I'll directly show you the. Okay. So if I give this optional argument oriented equal to true, so what this does is it assigns some orientations to the edges of G. Orientation means each edge it will direct either from Vi to Vj or Vj to Vi at random. Okay, this is randomly giving some orientation. So it is not, it is a particular special digraph. So generally when I say digraph, even though it's a simple digraph, you can have an edge from U to V as well as an edge from V to U. Because these are in different directions, they are not counted as multiple edges. But when I say oriented graph, it means in at most one direction there is an edge. There is a directed edge in at most one direction between a pair of vertices. Okay. So it is basically an undirected graph, but we are giving one direction to each edge. Okay. But without the opposite pair. A pair of anti-parallel edges or opposite directed edges are not there. So this is an oriented graph. So for oriented graph, the incidence matrix is a 0, 1, -1 incidence matrix. So the entry is, so there are two conventions. One convention is if your edge is oriented from say Vi to Vj, then by usual conventions that you find in most textbooks, the let me write it. Okay. Okay. By the way, there's a question in chat. Graph coloring, I'm not sure if I'll discuss. You can get the chromatic polynomial and such directly. Okay, so if you do G dot, oh, this is a markdown. So you can get chromatic number, chromatic polynomial, etc. Okay, I don't think I will discuss graph coloring in particular. Okay, so getting back to the incidence matrix. So I will not give the full definition. I'll just say Bij, right? The entry of Bij. Suppose Ej is an edge from Vi to Vk. Okay. Suppose Ej is an edge from Vi to Vk in that direction. Then Bij is equal to 1 and Vik is equal to -1. Okay, and other entries are 0. That's the point. If the jth edge is from vertex Vi to vertex Vk, that means the origin of the edge is Vi and terminus of the edge is Vk. Right? The head is Vi and tail is Vk. Then Bij is equal to 1 and Bik is equal to -1. So for, yes. No. Yeah. Here it is Kj. Sorry. Kj, not. Yeah, that is it. Correct. Kj, correct. J indicates the column number. So edges correspond to columns. Bij is 1. Bkj is equal to -1. Okay. So here, this is the usual convention. So by usual convention, this is saying that there is an edge from the second vertex to the first vertex, directed from second vertex to first vertex. That is one edge. That is the first edge. The next edge is from third vertex to first vertex. Okay. So in our indexing, it is vertex 1 to vertex 0, there is an edge. Vertex 2 to vertex 0, there is an edge, and so on. But Sage Math follows the opposite convention. So if I ask for this one, right, you get the opposite case, because we said it should have been 1 to 0, but now it is 0 to 1. Right? By the way, incidence matrix also gives you the graph. If you ask for graph of an incidence matrix, it will give you that. This is from 0 to 2 rather than from 2 to 0. That's because Sage Math follows the opposite convention. So if you refer to standard books like R.B. Bappett's book or Norman Biggs' book, there the definition is like this. This is the convention they follow. But Sage Math follows opposite convention. So you might want to take negative of whatever you're getting, right? So if you want the graph incidence matrix as per usual convention, just take minus of this. That will make it same. Okay. And of course, graph is still going to look different. That is the thing. I think there is an optional parameter that you can set for the convention. So I'll just check that. I forgot the code. Okay, and I don't think. Maybe I'm not remembering it correctly. So maybe you can't change the convention, but you have to take the negative if you want. Okay. So according to your convention, if you want it, you have to take the negative, right? Yeah. So now according to this, the edge is from 0 to 1. And here also, when you ask for it to show the graph also, again, Sage will follow the opposite convention, right? So there also you have to take the opposite. So minus of. So then if you define Q like this, is it related to any other graph matrix? Is there a relation between this matrix and any of the other graph matrices? Laplacian matrix, yes. So let's see what is Q times Q transpose. Q, you can write Q dot transpose like this, or just Q dot capital T also for any matrix. Dot capital T is a shortcut for that. As you can see, it's the same, right? And the surprising thing is that here you can see G has been given some orientation. The original graph is undirected, right? The Laplacian matrix is also defined for undirected graph. No matter what orientation you give, when you take Q star Q transpose, you will get the same Laplacian matrix. The Laplacian matrix will not depend on the orientation you have given, right? It's just an intermediate thing. It's like you are actually doing some computation with real numbers. For example, if you studied electric circuits, there you might do some computation where involving imaginary numbers, complex numbers, right? But finally, your answer is some real number because some value of current or something, right? Or impedance or something. It's some real number. So you do some intermediate computations involving complex numbers, although your final answer is still going to be a real number. Similarly here, although you are really working with undirected graph, for a particular reason, you're taking an oriented graph. which has some directions on the edges. But then finally, when you compute the Laplacian matrix, that will be independent of the directions you have given. The answer will always work out correctly. Okay. The rank of the incidence matrix, it will tell you whether the graph is connected or not. Okay. So the rank will be n minus 1, and where n is the order, rank of Q will be n minus 1 if and only if the graph is connected. And that is why rank of Laplacian matrix will be n minus 1 if and only if the graph is connected. Otherwise, the rank will be smaller. So the nullity, which will give you the multiplicity of 0 as an eigenvalue, that will give you the number of components. Okay. That actually is easier to prove using the oriented incidence matrix. Okay, so these are standard results you can see. Again, you can explore them using Sage. Okay, now I'll do a little bit of algebraic graph theory also. This is also algebraic graph theory, but it's linear algebraic graph theory. So we'll do a little bit of abstract algebraic graph theory. Okay, there are some very interesting things there. So you know some algebraic structures like groups and rings, right? There are vector spaces also, but generally, if you take vector spaces, we could study them over R or C. Right? Those are infinite. Whereas graphs, usually you study finite graphs. Right? So we'll consider groups and rings. There are some graphs that you can define on groups and rings, which has recently there has been much research on these graphs associated with algebraic structures. Okay. They have some nice properties also. That is the thing. So if you take, maybe before going to that, zero divisor graph, for example, zero divisor graph of a ring, or zero divisor graph of a semi-group also you can define. Okay, then Cayley graphs of groups, power graphs of groups, and there are some other graphs defined on group cycle graphs and so on. Yeah, before that, maybe we'll see groups as they relate to graphs rather than the other way. So if you already have a graph, then there is naturally a group associated with it, which is if you want to measure how symmetric the graph is, then you need to see how many automorphisms the graph has. So what is a graph isomorphism? First of all, we discussed it yesterday. It's a bijective mapping from the vertex set of one graph to the other that preserves adjacency and non-adjacency. So a graph is always isomorphic to itself because identity mapping on the vertex set is an isomorphism of the graph to itself, right? But there may be others also. So for example, if you take path graph of order 5. Right? One isomorphism of this graph from this graph to itself is, of course, 0 maps to 0, 1 maps to 1, so on. 4 maps to 4. But there's one more. Suppose you map 0 to 4 and 4 to 0. And then 1 to 3 and 3 to 1 and 2 to itself. This is also an isomorphism because initially 0 and 1 are adjacent. After mapping, 0 becomes 4 and 1 becomes 3. So now 4 and 3 are adjacent. That is true. 0 and 2 are non-adjacent, right? And after mapping, 0 maps to 4, 2 maps to itself. 4 and 2 are non-adjacent. That is also correct. Similarly, 1 maps to 3, 3 maps to 1, right? So 1 and 2 are adjacent. After mapping, 3 and 2 are adjacent, right? And so on. This is an automorphism. An isomorphism from graph to itself is called an automorphism of the graph. And this graph has exactly two automorphisms. Any path graph, right, other than trivial path with one vertex, any larger path graph has exactly two automorphisms. There is just this one. Either if you take the vertices as 0, etc., and minus 1, either each I goes to I, or each I goes to n minus I minus 1. 0 goes to n minus 1, 1 goes to n minus 2, and so on. These are the only two automorphisms. So here, if I ask for automorphism group, will give me. It is permutation group with generator 0, 4, 1, 3. So this is the cycle decomposition of the generator. So it happens to be a cyclic group of order 2. Okay, so I can also ask it to list the elements, I think. Let's see. So I'll just say pot P5. Right? So if I ask for the order of the group, it's 2. That's what we said. There are exactly 2 automorphisms, right? Yeah, it will explicitly show me the automorphisms also if I ask for the list. So this is identity mapping. Everything is fixed. This is interchange 0 and 4, interchange 1 and 3. 2 is not mentioned, means which means it is fixed. Okay. So interchange 0, 4, interchange 2, 3, fixed 2. Okay. This is the automorphism group of the graph. Right? If I change it to P6, for example. So its order is still going to be 2. If I ask for the list of elements, so interchange 0 and 5, then interchange 1 and 4, interchange 2 and 3. There is no central one, there's no one central vertex to fix. Right? So 0 and 4, 5 are interchanged, 1 and 4 are interchanged, 2 and 3 are interchanged. Right? That is the other, only non-trivial automorphism, non-identity automorphism. Okay, but let's see now cycles. So I'll take C5. Right. So what are some obvious automorphisms of this other than identity? Yes, you can rotate, right? You can rotate it. So 0 maps to 1, 1 maps to 2, 2 maps to 3, 3 maps to 4. That is 1. 4 maps to 0, right? So the cyclic, that's a cyclic permutation, right? 0 maps to 1, which maps to 2, which maps to 3, which maps to 4, which maps to 0. That's one cycle. And then, of course, once you have this one cycle, you can repeat it any number of times to get more automorphism. So 0 maps to 2 in 2 steps. 0 maps to 2, 2 maps to 4, 4 maps to 1, 1 maps to 3, 3 maps to 0. That is another one, or 0 maps to 3 and so on. So you get at least 5 different ones, including the identity. Any others? Reflections. You can fix 0, right? And interchange 1 and 4, interchange 2 and 3. So consider, so in this drawing especially, it's a regular polygon, regular pentagon. So you can consider the a line passing through 0 and bisecting this edge, right? And consider that as an axis and reflect this graph about that axis. So 1 and 4 get interchanged, 2 and 3 get interchanged. That is one reflection. So obviously there are 5 other, totally 5 reflections, 4 other reflections, right? For axis that passes through 1 and the edge 3, 4. Axis that passes through 2 and the edge 0, 4. Axis that passes through 3 and edge 0, 1. Axis passing through 4 and edge 1, 2, right? Bisector of, it's basically the perpendicular bisector of 1, 2, and so on. Right. So totally there are at least 10 automorphisms, and in fact, these are the only 10. So if I look for the automorphism group, it is a group of order 10. So if you list the elements, it's exactly these permutations. So this is a cycle which maps 0 to 4, 4 to 3, 3 to 2, 2 to 1, 1 to 0. Next cycle is 0 to 3, to 1, to 4, to 2, to 0. Then 0 to 2, that to 4, 1, 3 to 0. Then 0 to 1, to 2, 3, 4, 0. Then this is the reflection. 1, 4, 2, 3, 0 fixed. The other one, 0, 4, 1, 3, 2 is fixed, and so on. These are the 10. These are the 10 automorphisms of C5. So in general, for Cn, for n greater than or equal to 3, the automorphism group will be of order 2n. Okay, and it will in fact be the dihedral group of order 2n. Okay. There's a question about constructing a family of graphs using this other library. So I don't think I'll be able to discuss it in this workshop. Let me see. So by the way, there are apart from constructing graphs manually like this and using matrices and so on, suppose you want something like you're studying for some reason all strongly regular graphs of a particular order or all connected graphs of a particular order. We can generate random connected graphs as we saw, but you want all connected graphs. How to get those? Or all strongly regular graphs. So strongly regular graph is a graph which is regular, which means all the vertex degrees are same. And also there are two other constants associated with it, which is any two adjacent vertices will be commonly adjacent to some lambda number of vertices, that lambda being fixed. Any two non-adjacent vertices will be commonly adjacent to some mu number of vertices, again mu being fixed. So if these three things are fixed, the degrees are all same, the number of common neighbors of adjacent pairs, that is same, number of common neighbors of non-adjacent pairs of vertices, that is also same. Like these three constants are there. Once you fix them, you get a strongly, any graph with these three fixed is called a strongly regular graph. Okay. They also have some significance in the study of the experiment, the design of experiments, right? Statistical designs or combinatorial designs, right? So it's related to that also. And they have some nice spectral properties. They're characterized as those graphs that have exactly three distinct eigenvalues. If you have a graph with exactly three distinct eigenvalues, it's going to be a strongly regular. So suppose you're studying all strongly regular graphs. So what to do then? Either you have to write a code to generate them, which is also difficult. So there are some graph databases. Okay. That's probably not going to give you the correct result because self-complementary graphs is another example. You want all self-complementary graphs of a particular order. Okay. Yes. So there are, if you search properly, you'll get databases with these in a particular format. First of all, let me see if I've already bookmarked it. No, unfortunately, no. Yeah, you can see that this is already there in Sage. Okay, strongly regular graphs. Some of these databases are already there. Okay, let me see, the reference possibly has. No, not this. Also, there are some websites where these are available as files. Yeah, here, for example. Okay. So it will give you for very large orders also. These are parameters, but there are some websites where these graphs have already been found out, and then they are encoded in a particular format, which you can load in Sage. So if you want to take those graphs and then experiment with them, study whatever parameter you're studying, some spectral properties or anything, you can do that in Sage by downloading these files, which are like some encoded files, and then loading them in Sage. So there is a functionality in Sage for doing this. So maybe tomorrow I'll look up the database on the website and tell you what these are, right? So if you want to experiment with a large collection of graphs of a particular kind, these are already available. Okay. Yeah. So this is automorphism group of a graph. As you can see, you can get that. Tomorrow we'll see algebraic graphs defined on groups and so on. Okay. So I think we'll stop for today. Yes. Thank you.